Hello, good morning. So let us have the class summary now. So today we will continue our discussion on recurrence relation, and then we will actually be finishing this topic today. We will talk about another way to solve a recurrence relation, a linear recurrence, by using generating functions. So let us first revisit the two problems that we have studied before when we are using the characteristic equation method. So this problem is, suppose that we have n ovals in the plane, and then we assume that any two ovals will intersect at exactly 2 points and no three ovals intersect at the same point. How many regions do they divide the plane? For this problem, we have established the following recurrence. We have found that an is equal to an minus 1 plus 2 times n minus 1 in general. So the function of an actually grows quadratically, and then we have the starting condition a1 is equal to 2. So by using the generating function method, we are interested in the terms of a1, a2, a3. So we are going to create a so-called function, the generating function a of x, which is equal to a0 plus a1x plus a2x squared plus a3x cubed, and so on and so forth. What we want to do here is we want to find a closed form for this generating function of ax so that later we can calculate the coefficient of x to the power k for any k. So in that case, we can find the value of a sub k. Okay, so let us see a general way of how to do this. So for this particular example, a of x is equal to this form, and having this recurrence relationship, so what we can do here is we know that we want to have an multiplied with x to the power n. So what we are going to do so is we get the original recurrence relationship and multiply x to the power n on both sides. Okay, so we multiplied x to the power n on both sides, and we know that based on this an times x to the power n, we can create the generating function of a of x by summing all the possible cases from n is equal to 0 up to infinity. For this recurrence relationship, we know that we can do so for any n greater than 1. So in that case, if we try to sum this up, actually for any n greater than 1, right? Or greater than, yeah. So somehow there is a term missing, but the basic idea here is that when we sum up all the terms of anx to the power n on the left hand side, we can create something related to a of x. And when we do so by summing up things on the right hand side, for this one, we can see that it is also related to a of x. It is simply x times a of x. And for the last term, it is independent of the little a of I. So in that case, we can actually find the closed form for this one. So this is, let's say for this, we can find out that, oh, the summation of this one gives us 2 times x squared divided by 1 minus x squared. At this point, we have a relationship of ax with some function of x. So we can, by rearranging the terms, we can actually find out that a of x is equal to this one. So this is like I move x onto this side, so I will have 1 minus x times a of x, move everything on the right hand side, and then divide everything by 1 minus x, so we will get something like this. This is simple algebra. The good thing is that here we now have the closed form for ax. So based on this, it may be easy for us to compute the coefficient of x to the power n for any n. So using the generating function practice that we have done before, then we can easily find out that what is the value of a sub n. Okay, so this is the first example. Okay, one remark. So here, In the previous example, we have set a0. So this is actually the value of a0. So we can, if we set a0 to be equal to 2, then we will find out that the formula an is equal to an minus 1 plus 2 times an minus 1, it also works even for the case of n is equal to 1. So in that case, we can have a better way to do the summation here, so that this is truly x times a of x. So because it requires us to use a0. Is that okay? So in that sense, we can have a simplification when we are doing when we are using this method. But in fact, a0 is not part of the description of this original problem. We can actually set a0 to any arbitrary constant. But by doing so, we will have a harder time to simplify the equation. We will have two different cases. So when n is not equal to 0, we will have a0 is equal to the value that we want. But when n is equal to some other value, we will have other values that we want. So in that case, sometimes it may be nice to find out what is the best way to set up some value that is not required in the original problem, but then we can set it up so that it can be used to our benefit. Yeah, so this is an example, so you can go through this by yourself. Okay, another example here is, let us take a look of this string problem. We look at n digits quaternary strings, so each of the character is coming from 0, 1, 2, or 3. We want to find out how many of them contains even number of zeros. For this problem, we have a combinatorial proof before, so we can solve this by using the combinatorics. We can solve this by using the previous recurrence relation by solving characteristic equation. But for here, let us use this as an example to solve it by using recurrence and then solve the recurrence using generating function. We let an to be the number of n-digit quaternary strings with even number of zeros, and then we want to establish a generating function such that it generates the term a0, a1, a2, and so on. So this is the recurrence that we can establish. So we can establish that an is equal to 3 times an minus 1 plus 4 times 4 to the power n minus 1 minus of an minus 1. The reason is, in order to obtain an n-digit quaternary string with even number of zeros, one way is we can start with an n minus 1 digit string with even number of zeros and then append 1, 2, or 3 as the last character. So the number of ways of doing so is there are an minus 1 ways to create a string with even number of zeros of length digit n minus 1. And then after that, we have 3 choices that we can make to put the character as the last character. So there are 3 times an minus 1 ways of doing so in the first case. The other case will be, we have n minus 1 digit quaternary string with odd number of zeros, and then it is followed by a 0 at the end. So in that case, we will have even number of zeros in total. How many ways are there? The last digit, there is no choice. There's just one choice. And the previous n minus 1 digit, we have altogether 4 to the power n minus 1 minus an minus 1 choice. So this is like this. So we can simplify the problem as an is equal to 2 times an minus 1 plus 4 to the power n minus 1, or we have an minus 2an minus 1 is equal to 4 to the power n minus 1. Now, of course, here, this is an easy form. You can solve this by using the characteristic equation method. But what we are going to do now is solve by generating function. Okay, so we are going to establish a generating function a of x, which is equal to a0 plus a1x plus a2x squared, and so on and so forth. Now, but before we do so, we may have a choice to select the a0 that we want. to our benefit. We find that a of 1 is equal to the number of ways of one-digit string with even number of zeros. So there are actually 3 ways of doing so. So a of 1 is equal to 3. And then we want to have what? We want to have a of 1 minus 2 times a of 0 is equal to 4 to the power 0. So it would be great if we can have 3, which is equal to a of 1, minus 2 times a of 0 is equal to 1. So in that case, the best a0 that we want to make is, let's make a0 to be what? To be 1. Okay? Where is my slide? So in that case, it's good to set a0 to be 1. Now by setting a0 to be 1, then when we are doing the same thing, we sum up everything. So we multiply x to the power n to every part here. We sum up everything, and we will find that this is related to a of x. This is related to x times a of x, and we can compute the closed form for this one. So after simplification, we will have ax minus a0 minus 2 times x of a of x is equal to x divided by 1 minus 4x. And after rearrangement of terms, we find that a of x can be expressed as this one, and then we use partial fraction. We use partial fraction and find out that this is equal to this one plus this one. And now with the form of ax like this, it is fairly easy to compute the coefficient of x to the power n, and then we solve the problem. Okay. So by using that, we find that an is equal to half of 2 to the power n plus half of 4 to the power n. Okay. Now this time we have a more challenging problem. So we consider all the n-digit quaternary strings, and we want to find out how many of them contains at the same time even number of zeros and even number of ones. Now to solve this, let's say this is the focus that we want. Let's say B of n is the focus that we want. We want to find out how many strings are there with even number of ones and even number of zeros. Let's also do something more. So we can also define C of n to be the number of strings with even number of zeros, odd number of ones, and similarly D of n to be number of strings with odd number of zeros and even number of ones. Now what we are going to do is we are going to consider generating function for Bn, generating function for Cn, and generating function for Dn together, and then use algebra to find out what is the closed form for the generating function of Bn. Is that okay? So first of all, by easy argument, we can find out that B of n is equal to something like this. So we have a recurrence for B of n based on B, C, D terms. So this is not that difficult. So in order to get an n-digit string with even number of 0, even number of ones, we may do so like, let's begin with an n-1 length string with even number of zeros and even number of ones, and then we append 2 or we append 3 in the end. So we still keep even number of zeros, even number of ones. So the number of ways of doing so is 2 times Bn-1. Another way is we start with an n-1 length string with even number of zeros or number of ones. And in order to create even, then we have this string and then add a 1 in the end. So we get another one. So the number of ways of doing so is Cn-1. And similarly, the number of ways of having first n-1 digit with odd zeros, even ones, there are Dn-1 ways. And in order to create it, to make the total number even, then we add a 0 in the end. So the number of ways of doing so is Dn-1. So we establish a formula for Bn, and similarly, we can establish a formula for Cn, a formula for Dn. So this is just after simplification. We can do some simplification so that we are going to deal with a simpler equation. And what we are going to do here is that we multiply x to the power n to every term here. Based on this, we can get the generating function of B in terms of the generating function of B, C, and D. Similarly, generating function of C can be expressed as generating function of C, D, and this closed form, and so on. So what I mean is like this. We can get something like this. Now the term here, minus 3 over 4, minus 1 over 4, minus 1 over 4 is by setting B0, C0, D0 to specific values so that it can be used as our benefit so that we can avoid a lot of terms later when we simplify those things on the right hand side. So this is a clever choice of B0, this is the clever choice of C0, and this is a clever choice of D0. So after doing this, and then we can use algebra. And actually, if you watch this closely, actually C and D, they are actually symmetric. So we can actually find out that CD, they should be the same. And after solving all this together, yeah, you add these two, and somehow you can solve for what is the value of Cx. Cx will be equal to something like this. And once Cx and Dx are known, then we can solve for Bx. And so when Bx is known, then we can compute the coefficient of x to the power n here. So this is the value that we have. Okay, so this is the some examples of using the generating function, and we have actually more. So let's look at the set of slides, lecture note 6. Okay. So this time we are going to look at some special all the discussion are on linear recurrence, and here we look at nonlinear recurrence. But they are really special so that there is still a way to solve them using the generating function method. So the type of recurrence that we are going to look at is of some form like this. A of n is equal to A of n minus r times b of 0 plus A of n minus r minus 1 times b of 1, and so on and so forth. If you look at the subscript here, this is n minus r, this is 0, this is n minus r minus 1, this is 1. If you add up the number inside these subscript, they all add up to the same value, n minus r here. So this is usually called a convolution between the sequence of A and the sequence of B. Okay. And in particular, when A and B are referring to the same sequence, yeah, this is perhaps the simplest convolution that we can think of. So this will be the case of A of n is equal to an minus r minus multiply with a0 plus an minus r minus 1 multiply with a1, and all together. So this is the convolution that we look at. So we will, the last term will be a0. So this part from an minus r going down to a0, and the other part is it starts from a0 going up until you get an minus r. Is that okay? You need to have all terms appearing. Okay. Now for this kind of recurrence, so why is it good for us? So let's consider multiplying x to the power n to both sides. So we have x to the power n multiplied for both sides. If you look at things on the left hand side, we will get something that is related to a of x, the generating function a of x. If you look at the right hand side, now what is this term? What is this term? This is a0 an minus r multiplied with a0 an minus r minus 1 multiplied. So how do I get a term like this? This term is actually easily obtained when we multiply the generating function a of x with itself. When you multiply a of x with itself, then this term will be the coefficient of x to the power n minus r inside the product of ax squared. So this is actually also a term related to ax. It's not just simple ax, but it is ax squared. Okay, so in particular, if we look at the right-hand side, the right-hand side will be, this term is actually the coefficient of x to the power n minus x to the power n minus r. So we can replace this x to the power n by treating it as a constant term x to the power r multiplied with the summation of this one times x to the power n minus r. And what is the summation of this one multiplied with x to the power n minus r? So this is basically ax squared, or something related to ax squared. So in that sense, the right-hand side will be equal to ax squared, and then minus some of the terms that we have not counted here, because we are starting counting from n is equal to k. So we don't have the constant term of ax squared, we don't have the x term of ax squared, and so on and so forth. But we will start having the term of x to the power n minus k, we will start having the term x to the power k minus r as our first term here. So in that case, we will have ax squared minus this one, minus this one, minus this one, and so on and so forth. But it's easy. So if we do things carefully, we can find out that the right-hand side can be simplified based on the product of ax squared. Okay? So because of this, then we can establish the relationship that the left-hand side is this one, and the right-hand side is this one. So we will have a relationship of ax with the polynomial of x itself, and after that, we can solve for ax. So let's look at a concrete example. So suppose we have an expression with 5 terms, w1 plus w2 plus w3 up to let's say we have 4 terms. Okay, w1 plus w2 plus w3 plus w4. Now, the plus sign is associative. So to compute the value of the thing, what we can do here is we have different ways of doing so. We can add the first 2 together first, add the last 2 together, and then we add the 2 results together. So this is one way. We can have another way, we can have another way, and so on and so forth. So after careful counting, we find that there are exactly 5 ways of adding 4 terms. And in general, we want to find out how many ways to add n terms. So what should we do? So let us establish a recurrence relationship of counting the number of ways to add these n terms. So we let an to be the number of ways that we want to find out. The number of ways of an actually, so first of all, a1 is equal to 1. If we have just one term w1, there's no choice that we can make. But if in general, when n is larger, a of n, you can find out that it is equal to, we check out all the possible variations of the last plus sign that we have. For instance, in this case, this is the last plus sign. If this is the last plus sign, then the number of ways to do so will be how many ways of adding 2 values multiplied with how many ways of adding 2 values. Now, for this case, this is the last plus sign that we have. The number of ways of these cases, like 2 and 3, these are the 2 cases such that this is the last plus sign. This will be equal to what? The number of ways to add 1 value multiplied with the number of ways to add 3 values. Is that okay? So in general, a of n is equal to an minus 1 times a1 plus, there should be a typo here. This is not n minus r minus 1. Okay, sorry. So this is going to be an minus 1 multiplied with a1 plus an minus 2 multiplied with a2 plus an minus 3 multiplied with a3, and so on and so forth, up to a1 times an minus 1. Now notice that this is like really like a convolution, except that we don't have the term of a0 inside. We should have an, a0, a0, an. So in order to make it complete, so we One way that we can do so is we intentionally add A0AN here. We intentionally add A0AN there, but then we want to keep it to be correct. So a clever way is we set A0 to be 0. Is that okay? So in that case, in general, AN can be written as the convolution of the two sequences of A. And using the previous idea, we multiply x to the power n to every term here. So x to the power n here, and x to the power n to the convolution here. So we get something like this. The left-hand side here will be something related to a of x, the generating function ax. So this is ax minus the first two terms, a0 and then a1x. So we have this one. And the right-hand side, if we check it carefully, this will be equal to x squared multiplied with ax squared. Sorry, I made a mistake. So this is actually the coefficient of x to the power n here. Sorry, you don't need x squared. So it is just ax squared. But then, since we are adding things starting from 2, we should minus a0 squared, and then we should also minus a1a0 plus a0a1x. Now, luckily, we have set a0 to be 0, so this term is gone. Also, this term is 0 plus 0, so this is also gone. So this is also gone. a1 is equal to 1. So after simplification, we will have ax squared minus ax plus x is equal to 0. Now, if we treat a of x as a certain kind of object, we want to find out what kind of polynomial that ax should obey, such that we have this result. Let's use the algebra technique. So think of this as a certain object square minus this object plus x is equal to 0. So we can use the quadratic equation formula to find out that this object is equal to 1 plus or minus square root of 1 minus 4x divided by 2. This one comes from minus of b, okay, plus or minus square root of 1 minus 4 times the coefficient here, 1, the coefficient here, x, so minus 4x, and then divided by 2 times the coefficient here. So this is a quadratic formula in terms of this object ax. Okay, so in this quadratic formula, the coefficient of ax squared is 1, coefficient of ax is minus 1, and the constant term is little x. So we have ax is equal to this one. But we see that there are two solutions here, right? Either plus or minus. But we can easily find out that one of them should be rejected. So once we have one of them rejected, actually, the plus sign should be rejected because we require that a of 0 to be 0. So actually, it should be 1 minus this one. So after doing so, the general term will be something like this, and then we can solve for a of n is equal to 2n minus 2, choose n minus 1, and taking this term divided by n. Okay, now this term is a very well-known term. This is a term called the Catalan number, or this is actually the shifted Catalan number. Okay. So if you are interested in knowing more, so check out the OCW recording, and then we have a bunch of other examples. But then, yeah. So this is for fun. Okay, so it appears in really a lot of different combinatorial problem. Okay, for another type, so this is a more general type of recurrence. So this time, B of n is the convolution of the two sequences of A and then also B. Okay, so we have something like this. So we do the same idea. So if we have a recurrence that is already in this nice form, we can multiply x to the power n on both sides, sum things up. So the left-hand side will be something related to the generating function bx, and the right-hand side will be related to the product of the generating function ax and bx. Is that okay? And then we can do things similar. So this is the basic idea that we have. And in the lecture, we have explained how to solve a series of related problems called pattern occurrences problem using this method. So let me briefly introduce the problem here. So we have a binary string, let's say S, to be given as an input, and then we have a pattern P, and we define, okay, so we are going to define what is meant by an occurrence of P. So we are interested in non-overlapping occurrences of P. So the idea here is we are going to scan the string S starting from the left to right until we find the first occurrence of P. So for instance, let's say P is equal to the pattern 101 and S is equal to 1101, 1101, something like this. Then after we scan the first few characters 1101, we have discovered the pattern 101 occurring. So in that case, we take this as the first occurrence of P. We say that this occurrence of P occurs at position 4 because we have found out that after reading position 4, we see the full pattern P appearing. Okay, and then our focus is to get non-overlapping occurrences. So what we are going to do here is that we chop the first 4 characters and then start reading from the next character. So if we start reading from the next character, we will see 11101, something like this, and then we will find out that P occurs again at a later position. So we focus here in this case, like suppose that P is still 101, but then the original pattern starts with 10101. Then we will say that P only occurs at the position 3, but P doesn't occur at position 5. Is that okay? Okay. So this is the particular example. So P occurs at this location, 010, and after that we chop it off, and then we find that P occurs at this position again, and after that we chop it off, and then we don't see any P. So P occurs after reading the fifth, 1, 2, 3, 4, 5, after reading the 5th character, and also after reading the 9th character. Is that okay? So now we are interested in finding the number of n-bit binary strings such that the pattern 010 is detected when the nth bit is scanned. Okay, so in this particular case, for this pattern, P, which is equal to 010, it is discovered, or it is occurring when the 9th bit is scanned. But it is not occurring, or we do not find this pattern when the 7th bit is scanned. But we find this pattern when the 5th bit is scanned. And for this problem, we focus on the case that the string that we are looking at are all the possible n-bit binary strings. And among them, how many will have 010 detected at the last bit? So based on our notation, we use Bn to denote the number of such sequence. We can establish a relationship that B of n plus B of n minus 2 is equal to this one. So for this case, this is not very special. There is no convolution involved. So we can find out the value of B easily. So we can use this is the simple generating function method and find out that, okay, B of x is equal to this function. Okay, so this is generating function for B of x. And now, what is more, so what is the example for this special nonlinear recurrence? So let's make the problem now a little bit more complicated. So this time, we want to find out the number of n-bit binary strings such that 010 is first detected at the nth bit. So we don't just require 010 is detected at the nth bit, but we want it to be detected here at the first time. Okay, so here we let an be such sequence, be the number of such sequence, and bn to be the same as what we have defined before. And in this case, we can establish the recurrence relationship B of n is equal to something like this. Now this time we have A of n plus, we have a big jump here. We don't have an minus 1, we don't have an minus 2, but we start with an minus 3, b3, and so on and so forth up to this one. So if you look at this, this is something that is close to a convolution of the sequence of A and B, but we have some terms missing. And to solve this problem, we are going to complete this part by making this into some true convolution. So how can we do so? Without making this wrong, we hope to keep this to be equal. So we are going to have some terms invented here. We want to add the terms A0, Bn, and also A1, Bn minus 1, and then also A2, Bn minus 2. Add it here without making anything wrong. But it is easy. We can add things here freely by setting A0, A1, A2 to be 0. That's done. And on this side, you see An, but there is no An B0. So I want to make this An into An B0, and then I want to complete the convolution by adding An minus 1 B1 plus An minus 2 B2. So how can we do so? So this is also easy. We set B0 to be 1, and then B1, B2 to be 0. Then this is done. So by setting these initial conditions cleverly, we can complete the right-hand side and make it into a true convolution. The nice thing of doing so is, this time, b of x minus 1 is equal to a of x multiplied with bx. This is going to be very, very simple. And this is, by doing this setting, we do not violate any assumption that we make here. Here, we just need b1, b0 to be 0. We don't care about b0, right? So we do not have any contradiction with the things that we have derived here. So it is still consistent to the bx we have defined before. So we can make use of the bx that we have obtained before, and then we have this bx minus 1 is equal to ax bx, so that using rearrangement of terms, we can get a of x in terms of b of x, and so that we can get the generating function for a of x. Is that okay? And we can have some more examples later. So I think this is pretty much the same idea as we are studying. So I will leave this for you to check the OCW recording. Okay, so these are similar examples. Okay. And finally, we have also prepared something in the slides, but we have not discussed in the lecture. So this is the recurrence with two indices. So sometimes, for instance, this is the Pascal identity. So in Pascal identity, we have n, we have r, we have two terms as a parameter. And then we find that CNR is equal to something like this. This is the recurrence that we have. So we can actually make use of the generating function idea, and then see if we can get the generating function for C of the two terms here. So what we are going to do here is, we are going to make a two indices generating function, a of y of x, such that this generating function will have terms that has two coefficients. Rather, it is not just have a term of x to the power n. It will have a term x to the power something, let's say I, multiplied with y to the power something, let's say j, something like this. So we can now represent the value that we want here, the value that we want here, something like this. So let's say C of ij to be represented as the coefficient in the generating function with the value which is associated with the x to the power I, y to the power j power, something like this. And still, we can make use of our idea and solve for this one. So I will leave this for you as an exercise. So this is the generating function with two values. Yeah, with n and yeah. So I will leave this for you to check. Okay. I think that's all for what I want to show you today. So the last part, recurrence with two indices, we are not going to cover it in the exam. This is just for fun. Okay. Yeah, I think that's all for today. Thank you very much. Yeah, sorry for making this very long today. Yeah, thanks all. Thank you. And then see you next week. See you next Tuesday. Okay, bye bye. Have a nice weekend.